This talk is a combination of a couple of my obsessions plus an example of the sort of thing I do when I get bored. I'm the sort of person that tends to be busy an awful lot of the time. My wife says that I never get bored. Actually, the opposite's true. I get bored all the time, which is why I'm usually always coming up with daft things to do. And during the pandemic, I decided I would keep myself busy, and I had a couple of ideas, one of which was learning to draw, which is how I managed to actually do my own art for the slides this time. And also, I decided what I'd do is go and take some really old computer game, as it happens from 1975 in this case, and convert it into modern functional style C#. So this is my talk about how I manage that, and I'll try and keep it down into the time we've got. That's a link to my Twitter, my GitHub, and all the rest of it in the unlikely event that anyone would like to talk to me again, but feel free. So first off, briefly, what is functional programming? I'll just blast through these. It's a paradigm, not a framework, meaning it is a style of programming. It does not require any NuGet packages to be added or anything of that sort. You can write it in straight out of the box C# to some extent. It's declarative, not imperative. Now, what that means is declarative is a style of coding where you work more around defining what it is that you actually want at the end and worry less about how exactly it's stitched together. An example of declarative programming that everyone's probably familiar with is TSQL. Because when you look at a TSQL statement, do you necessarily care which order the operations are executed in? You don't. The first you write is a select, but I almost guarantee you that it's not the first thing to be actually executed most of the time. Imperative is more concerned with saying, here's how I start with an empty something, here's how I build it up step by step, and I'm very concerned with the precise order of operations. So object-oriented is imperative. So properties. These are the properties of a functional languages. Immutability, meaning that once a variable is declared and set, it cannot ever be changed again. Higher order functions sounds complicated. It's not. Functions passed around as variables. So func delegates is an example of that in C#. Expressions rather than statements. Right. So an expression is something that evaluates to a value. So any single line const where you take some old variables and put them together into a new value, that's an expression. Statements is things like ifs, whiles, fors. We don't use those in functional programming, and I'll try to minimize them to the greatest extent I can within C#. Referential transparency, also known as pure functions, meaning given the same values for the parameters to a function, it will always give the same result no matter what. Recursion, hopefully everyone's happy with recursion, otherwise this might be a tricky talk for you. Pattern matching, well, I used to have to explain that, but we've got it in C# now as of the last version or so. Switch expressions are pattern matching. And stateless, there is no state. This is one of the things that makes it very, very desirable for folks that want to work with things like async or multiple processing on the same queue, that sort of thing. So why? It's not talked about a lot, but my actual favorite feature is that first one, that is reduced code noise. Now, what do I mean by code noise? Well, there's a concept in audio engineering called the signal to noise ratio, where the signal is the thing you wish to listen to and the noise is the background that is undesirable. So it's the hiss on an old cassette. It's the rumble on a record. It's on a Justin Bieber album. It's the album. So whatever it is that you don't want to listen to. And I think an awful lot of object-oriented code tends to focus on what I would call the code noise, meaning the precise details of how I build this object from whatever. And I'm not really interested. What I want to know is, what are you trying to achieve, and get on with the job as fast as possible. And functional is much better at that. It's much more concise than object-oriented code. It's more testable. That's referring back to the pure functions. You can make pretty much almost 100% testable code to some extent. Some you have to make some acceptable gaps in that in C#. That's the way it is. It's more robust. It tends, once it's up, it tends never to crash out. There's all sorts of structures in place that will prevent that sort of thing from happening. It's more predictable, and it has, as I say, better support for concurrency, that is multiple processing, because there's no state. So that's the why. But this is C#. This is not F#. Even F# is not a pure functional language, but C# is certainly not. C# is somewhere in the middle. It supports both object-oriented and it supports functional. And because there has to be backwards compatibility, because there are certain constraints within C#, there's always going to be some areas where it simply isn't possible to write purely functional code. There are always some areas where we just have to sort of fudge something. And this diagram here is a demonstration of the two major parts of a shadow. Now, I've been learning drawing, so I know there's more than two. There's like 12. But there's two major parts of a shadow. There's the dark solid bit in the middle. That is it's called the umbra. And there's the grey fuzzy bit around the edge of a shadow. That's the penumbra. Now, in my world, the way I work is the functional bit, the purely functional bit, is the umbra in the middle. And I want to maximize as much of that as possible. And then the penumbra, the grey shady bit, is around the outside. That is where we have to compromise. That's where we have to make some allowance for the fact that not everything can ever be purely functional. And I try and minimize those areas and push them as far away from the rest of my code base as I can. And as I go through this talk, I shall point out one or two areas where I've had to compromise, because in C# that is simply the way it is. So on to Oregon Trail. Now, I had not heard of Oregon until I started doing this project, but it's a state in America, somewhere in the northwest, I believe. And this game relates to this part of American history, where wagons were sent from down the east coast all the way over to the west to Oregon to start, I don't know, farms or new lives or move into the city. I'm not sure, but the point is everyone was moving all of their goods across the whole width of America in these wagons pulled by oxen, and this is the concept that the game is based around. But moving on from there, because we have to, I've only got half an hour, so I have to whistle stop this a little bit, to the early 1970s, I think about the very, very early 70s. These two gentlemen were working in a university in America, the University of Dartmouth, and this is John Kemeny and Thomas Kurtz. Now, Kemeny is especially interesting for me from the history of computing perspective. He was an absolute genius of mathematics, but he was made head of mathematics at the university there, and he had an obsession with the idea that computers were the way forward. And he not only wanted computers to be considered important, but also he wanted computing to be made available for everyone. So these two, working together, implemented two absolutely incredible concepts. One was the idea of a timeshare. So computers prior to that were gigantic, huge basement-filling mainframes, and if you wanted to interact with them, you did a punch card and you handed it into a person who would then, at some point in the week, go down with a batch of these cards, feed them all into the machine, and then bring back all of the outputs. This is where the term batch processing comes from. And they implemented a system called time sharing, where there would be multiple terminals dotted around the campus at their university, and the computer would constantly switch its attention between all of the various terminals, giving everyone who worked on these things the impression that they were interacting somewhat live with the computer. So meaning that anyone could just sit down and actually have a go at doing some programming, which is absolutely terrific for us. And the other was, there we go, a programming language. The other programming languages of the time were things like Algol and Fortran, which I've never worked in personally, but I've seen examples of, and they are not terribly user-friendly. They had the idea that we would come up with a new programming language, something which was designed from the beginning to be completely user-friendly. And this is what they came up with. They wanted a verb to be put at the beginning of every statement to make it easier to tell what each individual line is doing. This was the basic all-purpose symbolic instruction code, or BASIC for short, or beginners all-purpose symbolic instruction code. And this was the first time that there was a programming language which was basically intuitive to read to some extent. It did also have the goto command, which has since become somewhat notorious. So anyone popping this into a computer and running it will actually find that this just runs an infinite loop. So not terribly clever. But they also had another brilliant innovation that they included in BASIC, which strangely enough was considered highly controversial at the time. And that's this command, input. It seems pretty much a given now that they will have some concept of input, but at the time it was a controversial thing, because a lot of folks were saying, well, computing only exists to do mathematics processing, so why would you break the execution of this maths chunking thing and take user input. But they persisted, and what happened was, on the university campus, everyone started using it to make computer games. Tons of them, loads. Apparently there were computer games that simulated things even down to American football. I'm not sure how exactly exciting that would have been, but probably at the time, considering that the alternative was, well, nothing or play American football, probably fairly exciting. And one of those games was Oregon Trail. And these are the sorts of machines that this was developed on. This is an HP Timeshare Basic terminal. And basically, this is a printer and a keyboard mashed together from our perspective. There is no monitor. There's none at all. There is no VDU. There's no concept of anything back then, not like we understand it. So what you would do is literally type in your commands to this sort of printer thing, and then the computer would print back the response. So when the code says print in old BASIC, it means it literally prints onto a piece of paper what the computer has done. But still, it was a world away from the old batch processing days. And these three gentlemen were the ones who developed Oregon Trail. They were student teachers, and they were teaching a course on the history of the Oregon Trail, and they had this idea that, well, we'll use the computer to make a computer game based on this idea to teach the students. And overnight it became a pretty wild, sensational hit on the campus, and everyone was playing it. This was in, I think, 1971. Now, that's them holding a printed off copy of their source code. Sadly, the 1971 version is lost to posterity. It was scrubbed along with everything else stored on the mainframe at the end of the semester, so it's gone. But in 1975, a Minnesotan education company approached them to create a new version, which they did. They reconstructed from memory, and that was released as the first official version of Oregon Trail released to the general public. And this series, Oregon Trail, is actually still going to this day. As far as I'm aware, there's been a new version released within the last couple of years. So it was, but this is the very, very most basic original form that is possible to find. And this is what it looks like if you run it on a DOS terminal. It's entirely text-based. This game is so old that it predates Pong. And this is kind of how games were in those days. And I certainly have fond memories of still playing text adventure games on computers that I had back when I was a kid. This is what the turn structure looks like. It's roughly speaking, it's a loop. We'll do some initial purchases, do our turn. You've got a couple of choices. You can go hunting, continue, or whatever. And then there's a couple of series of randomized events that may or may not happen depending on how far you are. There was even a hunting mini game with shooting. Now, I'll leave it to folks' imaginations to wonder how on earth you would do a hunting shooting mini game in an entirely text-based environment, but they did it, and I shall show you shortly. But basically, we just loop around this sequence of events again and again until we have reached Oregon based on a certain number of miles traveled per turn. This is what the original code roughly looks like. Now, the original thing was entirely text-based. I put a bit of color in here to make it easy to read. This color is purely my addition. This was total pure text in the old days. A dim is something which we still use in VB.NET, if anyone works in that, or at least in VB6 back when I was doing that. That defines an array, and in fact the dollar there indicates that this is a string. There was no concept of strings in old BASIC. You defined an array, and this text was stored into the array, which is what this is doing. What this is doing is saying, checking to see whether the user wants instruction, and if they type no, then we skip. This is another thing, is that things like ifs work by skipping lines. So most of the logic of an if statement was the reverse of what we do today. In the old days, it was kind of a case of, if this condition matches, then skip ahead. Whereas what we do these days is, if this condition matches, don't skip, and actually do. So I had to do an awful lot of reversing logic in order to make this work. Luckily, they created a set of commented code at the end, which told me what all the variables actually do. I don't know whether it was a memory saving thing or a convention, but basic applications tended to have very unhelpful variable names like these, single letters or 2-character names. So first bit of functional work I need to do is the interaction with the user. Functional is based entirely on predictable, pure interactions with other modules. There's nothing more impure than a human being, so this is the most important bit for me to replicate. So this is how it would be if I just went straight to the terminal. And look how happy that person is there. That person is happy because they play Oregon Trail. It is just that good. So first off, let's mock out the console with my own little interface. So at least we've got something vaguely testable we can inject now. That's great. But we want to go a few steps further. I want to actually be able to render the output from the console in a manner which I can handle. And this includes things like errors. This includes things like the user putting some rubbish in. And this is how I'd do it. I would say that there are three possible states to what comes out of the console. Something, meaning that the user actually entered some text. Nothing, meaning they just literally hit the enter button and entered nothing. That's a form of error state as far as we're concerned, or an error occurred. Now, I don't know what sort of errors can occur on the console, but still, I need to capture that. I don't want an unexpected thing to happen. And that's what that would look like. I'd have an abstract base class, and I've called this a maybe. Now, there's all sorts of other extra logic that can be applied to this. I'm keeping life simple for the moment. This is roughly an implementation of something called a discriminated union, but it's an idea of functional programming. So we start with the abstract base class, and then we have multiple implementations of that, which may have entirely or mostly different properties depending on which state we've hit. So the nothing actually has nothing inside it, because if they entered nothing, there can't be any variable. So in fact, I'm adapting this. This works better with things like the solid principles. I'm not putting anything in any of these states, no variable properties in, which aren't appropriate given the condition that's hit. And then reading lines might look something like this. We'll read a line and we'll check to see whether they actually entered anything. If they didn't, return a nothing. If they did, then return a something and contain the actual string that they entered within. And if they had an error, then we'll catch it. So what this means is, if an error does occur on the console, there will be no unhandled exception further on in the code because it was captured at this point, and the type of the object that we return tells us there was an error so that we can handle it later. And at the bottom of my screen here is an example of how I might handle that with the new funky switch expressions, which are one of the best features that's been added to C# in a while. And I can hit on something, meaning, and then I can give that message or nothing. And if there was an error, I can say that an error occurred, or maybe I might then tell the system to try again, whatever. But the point is that I know an error occurred, and I haven't had to create a metadata object with properties that I may or may not use depending on whether there was an error. And I can take this further and apply this to an operation. This is the same sort of concept, but where there is no actual return value. And all I want to return is, did this succeed or did this not? And if it didn't succeed, I want to make sure that an error is captured inside it. If it succeeded, then it can have no properties because it doesn't matter. And once again, we can do a try operation. I've done it as an extension method here to say, given a variable, we can attach a try operation function to it, saying try out whatever this is. And if it succeeds, i.e. it doesn't have an unhandled exception, return success, otherwise return a failure with the captured error. And this is how I do a write line. A write line doesn't have a return value, but I do want to capture if there was an error trying to write to the console. But I actually want to take this still a stage further and create a yet slightly more complicated discriminated union, where I want to differentiate between there being text or an integer returned. Now that's pretty much the same process as you've already seen. There we go. So I'll create this time what I'm returning is a user input type, which might still be empty, might have text or might have an integer, because there are different inputs at different parts of this game, and whether it's an integer or an input, an integer or a string is very important. And at different times, entering the wrong one might be considered an error condition. Most of the time, in fact, in Oregon Trail, it's integers that you want. So if the user enters anything else, we should consider that an error condition to be handled. And this is my code for my get input. So do a console.writeLine with whatever the prompt is, and then provided that the write result was not a failure, then do a read line, and then having done that, we'll convert that into a something, depending on whether it was a string. So we'll do our try parse there, and otherwise do an is null or white space check. So what this also means is that in the wider code base, things like the try parse on int, which normally I would have to do all over the code base because I need to check that it's int all over, is done in a single place in one code file, which then passes out something which has been abstracted meaningfully into whether it's an integer or not. And it just becomes a case of checking the result of this check that's already been done for us, rather than having to write out the try parse logic all over my code. So this is saving me an awful lot of time, and it ensures that I'm giving something out to my code base meaningful, rather than putting the onus on the wider code base to take the raw result and parse it, which is typically what we otherwise end up doing. And this is my complete replication of that first bit, which is to do a get input, saying, do you want instructions? Do a switch. If they said yes, then I've kind of changed the logic there to say, because it's a little annoying, because otherwise if you wrote anything literally other than no. I've also made it non-case sensitive. The original was case sensitive, so I think this technically works slightly better. And this renders that into a Boolean based on, was it text? Did they type yes? All other conditions, i.e. they didn't type text, they didn't type yes, will result in a false, in which case we're going to display the instructions. And there's the right message. Now this uses an if. That's a single line if, so I might even accept that. That's not strictly functional, because that is a statement. But for a single line, I might accept it like this. But I went a step further, because I wanted to see just how amazingly pure I could make this. So I made a method which I call write message conditional, which takes a Boolean to say whether I should write it or not, and a prompt, which is the prompt I'll write. So there we go. Write message conditional. I put it as part of the user interaction. So if they, so now I can say display instructions is a variable which I've already processed on the line before, and based on the results of that, I will determine whether to write this or not. So this is purely functional now. Great stuff. Then moving on to the managing of the inventory. Well, this took an awful lot more time, because we've got a series of purchases that need to be made in what was basically a form, where we go through each of these items, and this is roughly what it looks like. First, start with oxen, which you have to spend dollars on each of these. You have to spend between $200 and $300 on oxen. You have to spend a non-zero amount on all of the others, because there was a bug apparently in the 1971 version whereby if someone did a negative spend on any of these items, they could have all sorts of strange things happening. Plus, the total spend has to be less than $700, which is your initial amount of money. So there's sort of loops within loops, and each of these individual spends have a loop which checks to see whether you've entered something valid or not. And then there's the grander loop which says, did the whole thing make sense? In which case, loop back again if they didn't. And this is how you might do it in a more strictly object-oriented manner. So we'll get our input from the user. That will be check to see whether it's an integer, and is the integer between 200 and 300, because we're doing oxen at the moment. If it is, then good, we'll just return that. Otherwise, we need to tell the user something, not enough, too much, or whatever, using a switch expression, and then get an input from them to say, have another go, and carry on going while true. So we'll loop indefinitely until we get some sort of response back from them. But this is an indefinite loop using a while, and that's not strictly functional. So there are options for how we can make this more strictly functional. One is to use good old-fashioned recursion, like this one does. This get oxen spend function calls itself again. Now the problem with this is recursion is not terribly memory efficient in C#. If you recurse too many times, then you can explode the stack. So it depends how many times you think it's likely that someone's going to loop. If you think there's only going to be a couple of calls, you probably could do this. But if there's going to be hundreds or thousands of indefinite loop iterations, then you really need to stay away from recursion. So what other options have we got? Well, I created a function called iterate until, which implements this concept. So what I'm saying is iterate until a condition is met, which is down the bottom of the screen there. It's an integer between 200 and 300, and in the block of code before that is a func, which is what you do to actually try and get an attempt at the result. So it'll run the first function again and again until the result of the first function equals the second. So that's strictly functional, but how does that work behind the scenes? Well, it's actually a disguised while loop. This is a technique which is called trampolining, and frankly, it's a disguised while loop, because This is a compromise we have to make. If you switch over to F sharp, F sharp has features that allow you to do recursion without it exploding the stack, tail optimized recursion calls, but it's simply not a feature available in C sharp. And so far as I'm aware, there are no plans to ever make it available. So variations on this are inevitably what has to happen. I've looked into all sorts of possibilities, and to date, this is the best I've found, because all other options have other problems associated with them. So this isn't great, but at the very least, I'm keeping a single while loop in my code base. And if one day something becomes available in C# in a later version, then I'll simply replace this function with something more purely functional in whatever the new features are, and then we'll be 100% functional again. But for now, this is one of those fringes of code that I've had to push back. And then getting a non-zero spend is roughly the same process. That's for all the others. So all the other guys, the only thing that varies is the item name. So I can just write a single function for all the rest, and we'll do an iterate until they do something which is integer, which is greater than 0. So easy. Interestingly, resharper is underlining that that last line there. It's because it can't tell that it might not be a valid output, and it will be because I've coded it that way, but it looks like it's a step or two too deep for resharper to understand that no, it really is forced to be a correct input. And then I actually do just have a function which I call again and again, appending results based on collecting an array of items with an enum telling you which was the most recent item that you gathered, whether it was Oxford food or whatever, and based on whatever the last thing you did, then when next time we run this, we'll append on the new item based on whatever I expect to go next. That means I've got a whole batch of get initial inventory based on using trampolining to loop again and again, and there we go. Now I've actually used a little bit of recursion here to say to deal with the total spend being over 700, because at this point, to be honest, I'm not really very concerned, because I think there's only so many times that someone could go through the entire, fill in every single spend on every single item, and then find out you've overspent before they just flip the computer over and give up and try and play something else. So I'm not worried about using recursion here. And this is my play sequence. So I've used another structure here, which I call continue game. So continue game is based on something which Scott Blashin wrote a very good article on this. He called this railway-oriented architecture. I recommend looking on Scott Blashin's website, F# Fun and Profit, where he talks about this. And it's based on the idea that there are two possibilities, two kind of train lines, and every call to continue game is like a set of points. And the condition I've built into continue game is that you died in some manner. There is actually a cliche that everyone dies of dysentery, or I think it is in later versions of Oregon Trail, but actually that's not the case in the 1975 version. You can only die, I think, of hypothermia or injuries. So cheery, but it's not quite the same yet. But if you have died or you have won the game, that is game over, that's the condition down the bottom of the screen there, then do the function which is inside here. Otherwise, if someone has died, then just skip over, don't execute the function. So, for example, if we handle the riders on the trail, which is a sequence of events where you encounter some riders on the trail ahead, and you may or may not survive it, and you die at this point, then we move on to the next continue game call. That continue game call determines that you have reached game over, so we do not execute handle random events, and then the next one, cross mountains, we do not handle, and we simply exit the loop at this point. So it's an iterate until. So this is an incredibly simplified and not quite entirely completed version of something called a monad. It's not a proper monad, there are some other properties, but it's roughly the same sort of concept. And that's what that looks like. It's a tiny little extension method, but it's incredible how powerful this is. It means I can just define a single list of events and let them just be defined in one line, and I don't need to worry about doing all that boilerplate of checking after each one whether we should continue or not. So imagine just how much code that saves me. So I think I'm running out of time now, but I'll briefly talk about the shooting game. If everyone, I don't know if anyone's still interested to know how the shooting was done. It's like this. What you do is you literally type the word bang into the console, and using the enter command, it takes whatever you wrote it takes the time it took for you to type it, and then based on that, it records an integer, which is the number of seconds it took you to type bang, and it maximizes it to 7, and then that's used as a multiplier. So, and that sorry.
No, I was just laughing, Simon.
Oh, sorry. Okay.
At how it did that. So yeah.
Right. How am I doing for time?
You are up, I'm afraid.
Oh, right, okay.
I'm going to quickly give you a question because we
Sure.
don't have time for any, and
Wow.
it just touches on. Can you explain what a monad is? Now, we probably definitely don't have time for that.
Oh, so we're going for the easy questions, are we?
Yeah.
Yes, I can explain what a monad is, and oh goodness me, I don't want to go into technical detail about what on earth it is. The way I understand monad, now there are like 3 official formal definitions to a monad which have to be implemented, but I'm not going to go into that because that is really quite dull. But the way I take away from it is a monad is a relay race. So you've got a series of people, one after the other, and each person is a function, and they are each taking whatever the last person gave, whatever the output the last function was, and then themselves doing something with it and then passing their results on. But there is also a structure in there which says if someone failed at some point, you know what, don't bother passing this on, just kind of leave it as it is, and just leave this raw failed result and just tell everyone to don't bother doing anything, just pass it along to the end. So kind of like my continue game, you can define one train of function calls, but if something fails at some point, you don't need to do the boilerplate, check whether there was a null value coming out of it, check whether an error occurred. You can simply trust that the monad will know not to call any further functions. So it prevents you from having things like null exceptions or things like that might otherwise cause no end of trouble to your code base. There are better definitions, and I don't know if I can just do a quick plug for the book which I've got coming out, hopefully at the end of next year, where I have far more detailed explanations of all of these concepts. So this is coming out from O'Reilly next year.
Fantastic.
Still busy working on it at the moment.
Well, thank you very much, Simon. That was really interesting and fun. Lots of people said it was fun. So that is awesome.